They have a very interesting architecture that Mohammed Abdullah is going to take us through. And Mohammed is the founder, president, and chief technology officer with Soft Machines. And he started that back in 2006. Prior to that, he was with Intel, working on the Pentium Pro, and then working on Pentium 3 and Pentium 4. So he has a lot of background on processor architectures. So with that, I'm going to turn over to Mohammed to take us through the VISC processor platform.
Hi, everybody. About a year ago, we started what we went out of stealth mode and discussed Soft Machines architecture. Today, in the same conference, Linley conference, we are going to introduce the first product. And it's not the official launch of the product. It's really a technology disclosure. Shasta would be the first project that is going to be our first product. And it's going to provide you 2 to 3x IBC speed up or 4x performance, up to 4x performance per watt compared to other CPUs existing in the market. Last year, we introduced the 28 nanometer VISC architecture, the prototype, and we showed a similar type of IBC improvement. And we continue now to deliver the actual product, but we'll talk about the difference between the prototype and the product. Shasta and Mojave. Shasta is the microprocessor. Mojave is the reference SoC platform that goes with it. The key message that Shasta is able to deliver server class performance at a mobile power envelope. And that is unique value today in the market, and will be, our estimation will be unique for some time to come. Mojave is the SoC platform, the reference platform that goes alongside the Shasta processor. And it's going to be scalable from smart mobile to servers and provide you that scalability so that it can be deployed in different market segments. Both Shasta and VISC will be officially launched in 2016 and available for customers to pick up during 2016. The business model, people ask us about what is the business model. So we are not going to sell chips directly in the market and compete with chip makers in the market. What we will do is two types of business model. One of them is licensing the IP, different type of licenses, obviously, implementation, architecture, and technology, and also provide the customized solutions for people who want to vertically integrate, so co-develop, customize the SoCs so that people can deploy it in their actual solutions. This is a review of what we talked about last year in terms of the VISC architecture. So how is VISC architecture different than typical architectures? You see that you consume typical guess code. It could be single thread, could be multi-thread, but the interesting thing we'll talk about today is the single thread. We're showing here a virtual software layer. We didn't talk about it last time because we wanted to focus on the hardware where you get almost most of the performance out of. The virtual software layer primary goal is to provide support for legacy software. So basically, you'll be able to run your 20 years old binaries of particular ecosystem. And the software layer convert that. It's a lean and mean type of conversion layer. It will convert that guest ISA into VISC internal instruction set, virtual instruction set. The hardware is also unique in the way that you will see what we describe here. The first thing the hardware employs is what we call global front end. And the global front end goal is really take that single thread. It could be also consuming multi-thread, but in the case of single thread, it will take it and create what we call threadlets, which are kind of group of instructions, high abstraction of work group, and then distribute those threadlets among the different physical cores. Of course, the single thread will be always managed by one virtual core, and that virtual core will be able to distribute those threadlets to the different physical cores underneath in the hardware. And of course, that can give you the scalability in a more linear way. two cases here, scenarios that we're showing. On the left hand side, you see the single thread, what we call heavy app, in case of you have a performance demanding application. A virtual core will take responsibility of that heavy app, single software thread, and then manage all the resources in the physical cores in terms of coordinating, communicating, and orchestrating the work. And so you would be able to use the resources across the multi-core for that single thread, which is a unique thing. On the right-hand side, it's a multi-threading scenario. You will have two threads. In this case, we are showing. One is performance demanding. The other one is a little bit less performance demanding, so heavy and light application. The heavy app get hosted by the virtual core 1, and the light app get hosted by the virtual core 2. And in this case, the heavy app, where the virtual core 1 is managing, is taking more resources across the two cores, as much as needed to execute or respond to that performance requirements. And the light app hosted by virtual core 2 will only take a portion of that. The interesting thing about this load balancing of the multi-threading execution is that it happens dynamically. As the programs execute and as they go through their peaks and valleys of performance, the virtual cores can expand and contract, consuming more or less of the physical cores underneath. So it gives you that perfect dynamic load balancing without software, OS, kernel, or anybody actually muck with that or interfere or try to migrate something from one core to the other. So which is an interesting fine-grained type of load balancing. In terms of the efficiency, which is another. So performance is one thing, and we claim to have the highest IBC in the market in terms of ability to scale single thread and also ability to dynamically load balance the multi-thread and get the most benefit out of it. But also the performance efficiency is a very important aspect. And here we are showing typically, if you have, let's say, a single core trying to execute that single thread that we talked about, the only way that you could really improve the performance is by doing frequency scaling. And that comes with a voltage scaling, actually square of the voltage scaling. As you go and increase performance by, let's say, X, your power gets proportionally amplified by something of the order of X cube, obviously, because F times F square, V square. So that is the nature of this curve. It's the cubic nature of the curve of getting performance at a very high expense of power. The virtual core concepts of what VISC is deploying is basically whenever we need more performance, instead of going to voltage frequency scaling first, we go to employ more resources across the adjacent physical cores. And here there is a typo. These are actually two physical cores consumed by one virtual core. But we will obtain more resources from the next physical core and get to the performance. And this is why you see mostly linear performance power relationship. Only at the very end, when you still need more performance, we can do a little bit of voltage frequency scaling, and then you'll see something similar to the nature of the cubic, but it's really delaying that cubic effect until the end and stay linear as much as possible. The market place or the market segments that VISC architecture platforms can address is really quite versatile. We can scale from IoT gateways all the way to cloud, going through high-end smartphones, mobile, and desktop, and networking in the cloud, of course. And the reason is because we provide both the performance efficiency, that very significant performance per watt advantage. So it can allow you to go in any of those. And of course, we have the muscle in terms of pure performance to cover even the high end of the market segment. And there is a typo here. Again, 2 to 3x IBC improvement, 3 to 4x performance per watt. I don't think you guys still have the material, but the material will be available later today, so you'll be able to check all that stuff. Here is a quick overview of our roadmap. So last year, like we said, we introduced the VISC concept. So end of 2014, 2015, the prototype was showing a 28 nanometer prototype, 32-bit, and then the SoC reference design that went with it. In 2016, Shasta mid-2016 will be available alongside Mojave, which is the SoC reference platform, and it will have ability to support, like we said, one single thread or two single threads using one or two virtual cores, employing two physical cores. It could also be scaled as SMB type of thing by duplicating two Shasta processors together, hook them through coherency. It's a 64-bit and 2 gigahertz. It's a 16 nanometer. And then Mojave reference platform will be customizable. We'll talk about some of the features. The I/O interface will be 16 nanometer. We will provide a scalable solution, employing more virtual cores, improving both single thread and multi-thread performance in the years to come. Shasta Plus would be the next one, and then Tahoe would be in 2018, and providing the related SoC reference designs along them. So what is Shasta VISC processor? What does it contain? It supports both single and dual virtual core, provides that load dynamic balancing and the scaling of IBC. It's a 64-bit ISA, so we went from 32-bit to 64. Of course, that gives you the larger addressing memory space and the larger register. So pretty much it's capable of scaling to those market segments where it requires that. Pretty much today, everybody is going 64-bit. It supports multiple guest ISAs. So one thing we talked about before is the ability to support guest ISA, meaning you can run your legacy software. And besides supporting the VISC native ISA, which is our own native instruction set, we'll be able to support two other guest ISAs with Shasta. And that's going to be an interesting thing for people who want to deploy it in different ecosystems in the marketplace. It's a 2 gigahertz. It can run up to 2 gigahertz frequency. It's a 16 nanometer process. Obviously, this is a big jump from last year prototype, which we talked about in terms of being able to run up to 500 megahertz. A lot of people, when we came out last time, they were talking about performance of this high IBC that we obtains because we're running low frequency, and some of them actually predicted that we lose most of that gain when we run at the higher frequency. And Shasta is actually a proof that we are able to run high frequency but still maintain that advantage in the high IBC, high performance. You could scale that into SMB, so we provide also an SMB beside the virtual cores. We have SMB support, our own coherency protocol, and the amount of L2 caches that is available with each physical core is 1 meg per physical core. We have an interesting flexible system interface unit because every ecosystem uses a different system interface. So our own generic high-speed bus is 256-bit read-write bus adaptable to customers. As we said, we have our own coherency, and then you can adapt that to any standard bus interface like AMBA, OCB, or Core Connect. This is Shasta microarchitecture block diagram. So here we walk through, like we said, it's a 2 physical cores, and it's very interesting to see, the differences between this and a different microarchitecture. So the front end is your typical fetch units and instruction assembly. The threadlet formation is the unique thing where we actually, get instruction, group them together, and form what we call the threadlet, in which it get then scheduled, allocated into the different physical cores. So core 1 and core 2 can actually consume from either side of the global front end. Global front end is up to that threadlet formation, and after that, threadlets get allocated, scheduled, and dispatched across the 2 physical cores. And of course, they also communicate with memory, the regular L1, L2 type of hierarchy. Of course, the physical cores also can consume from across each other data. So that's an interesting, major difference also. Here as we talk about the pipe stages or the pipeline of Shasta, your front end, your fetch, consumes the regular, type of instructions, and 3 stages to actually be able to get the data. The front end is more tightly coupled, the two physical cores more tightly coupled, so that when we are consuming single thread, they can act together to consume that single thread. And then 3 stages is for that threadlet formation. So it's a unique and sophisticated piece of hardware. And then 6 stages to do allocation of threadlet, scheduling, and then dispatching to the different physical cores. And we show here 1 cycle is needed to cross across the 2 physical cores. If you are dispatching from each of the front-end side to the other physical core. Execution can take 1, 2, or 4 cycles depending on the complexity of the instruction. And then memory, of course, is a 4-stage latency. Here we show ability to build a node, a coherent SMB node out of 2 Shasta processors. This is 1 Shasta processor having those 2 virtual cores and 2 physical cores. And they connect through our own coherency support. So this is an SMB node. And then that SMB node can even scale further. If you want to put multiple more numbers of cores, you can scale through that flexible system interface unit using any coherency protocol standard, depending on the ecosystem that is being deployed in. So customers can, customers or us can make this interface unit talk to their own internal protocol, and then can be scaled, however they want it to be in terms of, flexibility and scalability. Here I'll talk about performance. This is actually the Spec 2000 scores. Very important point about these scores is we try to normalize the different processors that we simulated here. And all of these are in the marketplace today, and they represent the 2 wide, 3 wide, 5 wide, and 8 wide. They represent processors actually in the marketplace, and people will be able to associate those with classes of implementations. The important thing is we try to actually make an apple-to-apple comparison, something that is fair across all those, so that you don't get performance amplified by certain use of compiler, or large use of NL3 cache, or different node implementation, somebody 28, somebody 16, somebody 14. So we try to normalize all that stuff. So this is a GCC compiler as much as we could normalize to it and adjust if it is not a GCC compiler. 2 meg cache, again, right, whenever there is a 2 meg, adjust slightly if it's a larger cache, and then adjust the power and frequency to the 16 nanometer, TSMC 16 nanometer. And you can see that as you grow out in the out of order side, you are getting more performance, but within the same out of order width, you are getting that cube effect. So this is actually an interesting way of how can you think that complexity, the power versus performance. You are cubic within a certain voltage frequency, certain microarchitecture, but you are quadratic as you jump from one width of out of order to the other. And here we are showing, so hypothetically and magically, if you take that single thread and you divide it into 2 cores of each one of those, so a 2 wide becomes a 4 wide equivalent dual core, what is the performance and power efficiency? And you can see that if you really were able to take a single thread of any of those architecture, double the core and run it efficiently magically. We call it magically because single thread will not run on 2 cores, obviously. You'll get some curve, efficiency curve like that. But of course, this is hypothetical and magical. But let's see where VISC lies on this thing, right? We can see that VISC is exactly doing that type of thing. It's taking 2 physical cores, 1 single thread, and magically run that single thread. And this is why you are seeing that we are actually getting close to the curve of the dual core in terms of performance per watt efficiency. So this is kind of a testimony to the VISC architectural benefit compared to any microarchitecture that you will pick in the market. And we can see actually that as people in the market go towards the high end of the single thread performance, the 8 wide machine, I get there, they will get close to this performance per watt curve. And of course it has the benefit over there, while Shasta has the benefit across actually a wide range of power envelopes covering from mobile to server. And that's why we say, even at this level, you'll get a server class performance at a mobile power envelope. And that's exactly what is the message, the clear message that is differentiate VISC architecture than any of the traditional architectures in a unique value. We'll talk briefly about the VISC SoC platform. So like I said, Shasta as a microprocessor comes with a reference design that is a high performance that allows it to scale also from the low segment of the market to the high end of the market. We can easily add or delete devices in this SoC, and it's a robust design methodology, so turnaround time is pretty quick. It's a high performance even at the low end, and it can scale with that high performance. We provide more than 200 gigabyte per second coherent fabric on the SoC, so that includes the important devices on the coherent bus, including the CPU, obviously. About 40 gigabyte of DRAM, dual channel DDR4, so it's the latest memory technology, and then ability to connect to an L3 system, L3 cache, about 200 gigabyte per second. High bandwidth network and storage connectivity, and high performance multimedia and graphics. We'll talk a little bit more about it. We support industry standard APIs and IP blocks. So, OpenGL, OpenGLES, OpenMax for video, OpenCL for, accelerating, parallel performance, SATA and USB and gig Ethernet. We have a unique value also in the SoC. It's even though it's going into platforms that are not standard PC, it provides a unique value in terms of plug and play. So it's kind of like your plug and play devices in the PC, but bring it into the other market segments, including phones and convertibles and tablets. And it does provide security and virtualization blocks there, and it has a management system as well, remote management. This is kind of the block diagram of what included in that reference design, and of course we can add or delete from it based on the market segment. And you can see that there is a really fast memory system. We have support for visualization and security, enterprise, management, trusted platform, remote management, encryption, decryption hardware. We have also the network. We have the GIGI. We have the SATA. We provide PCIe 3, multimedia graphics. We have the latest Imagination core. It's not an announced code yet, but it can be running OpenGLES 3.2. And we have 4K video decoding and encoding. We have audio DSP. We have image processing, 20 megapixel. And we have also audio codecs and triple 4K display. So it's pretty updated and has the latest technologies in the marketplace. And of course, the Shasta quad-core VISC CPU, like we said, 2 Shasta SMB processors. So in summary, the VISC architecture provides that high-performance single-thread, highest in terms of the IBC, highest in the market, and scales to high frequency. We run to up to 2 gigahertz, and you can scale that even further with the optimized implementations. It's applicable to multiple segments in the market, scale from IoT gateways all the way to the cloud. And the first VISC product, which will be Shasta plus the Mojave reference platform, will be announced in 2016. Like we said, we actually don't put the chips in the market. We work with customers who both like to license the processor, or license the technology, or license the reference platform to integrate it within their solutions. And from smartphones to mobiles. And if you guys have any more questions, you can talk to us. We are available. We'll be here also after this presentation. Thank you very much.
All right. Thanks, Mohammed.
Thank you.